Polynomial and rational functions, there's this wholesome group of students who are very excited to learn about them, but they're a little bit too wholesome for me, so I put these guys there instead. Now we're going to learn about complex numbers. And I just made a PowerPoint. Did I start recording? Did I start recording? Uh-oh. I think I did. Let me see. Yeah, we're going. We're live here. So this PowerPoint, please don't write down every single thing. Here, I just kind of stole parts from their PowerPoint, and I have some of my own examples. The book used to have PowerPoints; it doesn't anymore. But most of you know about I, right? You guys know about I? I do. I is back in the day when they're, whoops, what happened? Technology, great. So back in the day when mathematicians went to solve equations, and one of the solutions would have a negative square root inside of it, they use that to define I, okay? And this is all the stuff you're going to learn about, okay? Don't worry about that. So let's move on to the imaginary unit I, okay? So that's what it talks about. The square root, I'm going to kind of buzz through this pretty quick, but I is the square root of -1. Most of you know that? Yep. Okay? And so if you know that, this is kind of a good thing to know. If you know that I is if I is defined as the square root of -1, that means that I squared, what's I squared? I squared is just -1, okay? And then I cubed is, it would be -I because it's -1 times I, so it's -I. And I to the fourth is, anyone know? 1, because that's I squared times I squared, right? I to the fourth can be written as I squared times I squared again, yes? Which would be I to the fourth, and I squared is -1, so -1 times -1 is equal to 1. Then the whole pattern repeats itself. So I to the fifth would be 1 times I, would just be I. And I to the sixth would be -1, right? And I to the seventh would be -I again, right? And I to the eighth would be what? 1, okay? So if they ask you what is I to the 267th power, could you figure that out? How? Yeah, divide by 4 and see what your remainder is, right? So it repeats itself so what I would do, I take 267, because this is always, 267, right? 267 divided by 4, right? So 4 goes in there 6 times, right? Is that right? Good, 2 left over. 4 goes in there 6 times again, right? Remainder 3, right? So what that means is going to hit, so after every multiple of 4, it's going to hit here, and then you count 3 more places, okay? So you go 1, 2, 3. So that would be the same as -I. You understand that? Yep. Okay? Just see how many times it goes through that cycle, and every 4, it ends up here, right? So then with your remainder, I would just count that many places past there, and so on. Yeah? Easy enough? Okay. So the next thing, imagine you obtain this set of complex numbers. I think that's the next slide. Okay. So complex numbers are, they have a real part and an imaginary part. Okay. And so complex number is anything of the form a plus b I, where this is the real part, and this is the imaginary part. Imaginary part, okay? So for instance, This is standard form. You put the real part first and then the imaginary part second. So negative 5 plus 3i is a complex number. Pure imaginary number, pure imaginary is a number like 3i or negative 2i. A real number is also considered a complex number, but you could have a real number like 5 or negative 7 or 6 2/3 or something like that. Those are real numbers, but they are all a subset of complex numbers. So if this is like a Venn diagram, here's all complex numbers, okay? Here's all real numbers, and here's pure imaginary numbers, pure imaginary. Okay, and then floating over here would be things like my 5 plus 3i. And then here would be like my pi and 6 and things like that. And over here would be like I and 2i and so. You get that? Easy enough? Okay? So the whole set of numbers is called complex numbers. And I listened to it, I think I talked about this before, but complex numbers, they have a lot of real life applications like in circuit design and in aerodynamics and things like that. They use imaginary numbers all the time to solve higher order equations. I just talked about this, so I'm not going to talk about it again. Okay, real numbers, I'll put a little dot on here so that it could be part of my notes. If I don't draw it in there, it doesn't become part of my notes when I post it. Okay, so what's next? Two complex numbers or names are equal to each other if and only if a plus bi is equal to c plus di. So they have to be exactly the same. If and only if this a here is equal to this c here, and b is equal to d. That's all that says. Questions about that? Makes sense. Okay. Operations. This is where it's fun. Okay. When you add complex numbers, you add their real parts and then you add their imaginary parts. Same thing with subtraction. Okay. The additive identity of a complex number, you just take the opposite of it and it would be equal to 0. I'm not sure if I have an example coming up, but I'll do one here. So if I have 3 minus 2i, and I add to that its additive inverse, what would be its additive inverse? Negative 3 plus 2i. I just multiply these by negative 1. Negative 3 plus 2i is going to give me out what? 0. Okay? That's called the additive inverse. Okay? Easy enough. Piece of cake so far. So you have, what's down here? So you have a plus bi plus, there. I talked about that already. Going too fast? Okay. Perform the operation. Could you do that? Let's do it. Okay? So you add together the real parts and the imaginary parts. So there's actually 3 complex numbers here. This one, this one, this one. So you have the 3 plus 2 plus negative 5 would comprise all your real parts, right? This minus minus, I distributed that through, okay? Plus negative 5. Plus the imaginary part, I'm going to put an I over here. What goes in front of the I? Negative 3i, right? Because you have to remember you have to distribute this negative sign. Negative 3i plus I. Whoops. Sorry, I shouldn't put a negative 3 plus 1, right? Negative 3, because it's negative 3i plus 1. And so altogether, I have 5 plus negative 5, I have 0, right? Minus 2i, which can be just written as negative 2i. Yeah? Did I do that right? Did I do that right, Colton? I think I did. That's 5. And that's minus 5. I did it. Okay, let's see if they tell me if it's right. Oh! Look at that. You have associative property. I'm going to put it down on here. Write everything down you see. No, don't do that. Many of the properties are valid for complex numbers as well. Here are some examples. Associative property means you can group things. Commutative property means you can flip them around. Like A plus BI is equal to BI plus A. Same thing works with multiplication. Doesn't matter which order you multiply them in. Distributive property. Notice how these, so let's look at an example they give us. Okay? Oh my goodness. Good enough. Okay, you can look at that. We'll do some examples in a second, so we're not gonna. Distributive property, what does that say? A plus B, so they multiply to A times C plus BI, and BI times C plus DI. A times C, A, so distributive property 2, I guess. And then we'll work on this as we do some. But when you do multiply complex numbers, you have to FOIL, okay? Which we're going to do in a second. So if I have this, you know how to do that? No. First, outer, inner, last. Trent, wake up. Do you know this already? Okay. So this times this gives you 9. This times this and this times this. What happens to those two things? So those are known, which we'll talk about in a second, as complex conjugates. Okay. So if one is 3 plus 2i and the other thing is 3 minus 2i, the middle part disappears, and then I get minus 2i squared, and then you simplify. And this goes away, right? And you get 9 minus 2 times what's I squared equal to? Negative 1, which is 9 plus 2, which is 11. Okay? So, did I mess up? It would be 4. Yeah, I knew that. I knew that. So you know, I knew that. That should be 4i squared, not 2. Okay? Someone said 13. I said, oh, that person's wrong. But I was wrong. Okay? So that would be 4 times negative 1. And that'd be negative 4 times negative 1, which makes 9 plus 4, which is not 11, but is actually 13. Okay? Questions? Easy enough? Have you done this before? When you multiply by a complex conjugate, it makes the imaginary part go away. Okay? Which is what you do when you simplify radicals. Okay? What's going on? So 3 plus 2i squared, you want to try that, or should we just go on? Let's just go on. Okay? Complex conjugates, I just talked about that. A plus 2i times a minus 2i makes things disappear. Okay? So you can remember this formula if you want. But a squared, a plus 2i times a minus 2i, the middle terms disappear, and you're left with a squared plus b squared. So if I add 3 minus 6i squared, no, not squared, sorry, 3 minus 6i times 3 plus 6i, all I have to do is, using this formula, it's just going to be this squared plus this squared, which is just 45. Yeah? Understand that? Okay. I mean, you could do it out the long way, but that's all that says. Okay? Multiply the complex number, you can do that. So this, we're seeing they are not both 0 multiplied. So this is, you want to, if they say simplify this, usually what they want is no i's in the denominator. It's kind of like not having any square roots in the denominator. So to do this, you multiply the top and the bottom by the complex conjugate. So I'm going to multiply the bottom by what? 1 minus 3i, and the top by 1 minus 3i. And when I do that, we just showed that this bottom is going to be equal to what? 10. Everyone see where the 10 came from? It's this squared plus this squared. And then you have to FOIL the top. Okay? And when I FOIL the top, I get first gives you 6. 2 outer terms give you negative 18i. 2 inner terms give you negative 2i. And the 2 last terms give you plus 6i squared. So when I simplify 6i squared, that's correct. So altogether, I get that that's equal to 6. I squared is negative 1, so I get minus 6. So I get 6 minus 6 minus 20i. That whole thing over 10. These go away. And I get negative 20i over 10, which could be rewritten as what? Negative 2i. That's kind of cool, huh? Okay, so that big mess turns into this little simple expression. Are we done yet?
Yes.
We're getting closer. Good. So what's next? Write the quotient. You can do that. I recently had this on a block games, having you guys practice as I went. That's what this little thing is with you guys would have to respond on your devices. It's kind of fun. But now we're going to talk about complex solutions to a quadratic equation. Okay. So now this isn't hard. You've done that. I think you've done this before too. When using quadratic formula, you often attain a result such as negative square root of 3, which you know is not a real number. By factoring out I, you can rewrite this number in standard form. So if you have like negative square root of 3, that can be written as root of 3i. How can I rewrite, for instance, negative square root of 27? Can you tell me how I could break that down? With i's. Colton?
Oh, it's square root?
Yeah, square root it.
Oh, 3 square root of 3i.
There's that. Very good. You did that in your head. Okay, that's fine. But it's square root 9 times the square root of negative 3, right? Which can be written as 3 times root of 3i. Yes? Can you do it, right? So you're simplifying radicals. There's a perfect square in there, 9. So I pulled that out. I left this here. And I pulled out the square root of negative 1 from the root of 3 to write that. Okay? Going too fast? Obey? Not going too fast. All right. So if a number is positive, print the square root of negative. We just talked about that. Another thing, if you, so if people have trouble with these things, if you multiply square roots, you can do it this way, okay? Or you could just multiply this straight across. What's negative root of 3 times negative 12? Positive square root of 36. Uh-oh. Which is equal to 6, right? So if I just use, so if I have something like this, you have to be really careful, okay? Because first you have to rewrite this as this, then you multiply the real parts together, and then you get an I squared. I squared is negative 1, so this is negative 6. So this would be wrong. So you can multiply square roots, but you can only multiply them if they're positive. Okay? And so you got to be kind of careful with that kind of stuff. Over here, they wrote this is root of 48i, root of 27i. Root of 48i can be, there's a perfect square in there, right? What perfect square is in 48? 16. 16 times 3. So I could write this as 4 root of 3i. And I could write this as 3 root of 3i. And you can add together these things because they're like terms. 4 root of 3i minus 3 root of 3i is equal to what? Root of 3i. Just root of 3i. Okay? I. Aye, aye.
Oh, Mr. President,
Yes.
do they have to be in that order as long as it is in different orders?
What do you mean? Can I
Like, could it be like
put that there?
I root of 3, or does it have to be like that?
I root of 3 is fine, yeah.
Okay.
I root of 3 is good too, because then you could tell that the I is not under the square root thing, but they write it like this. Okay? Aye, aye, aye. Okay, and the last thing is solving quadratics when you have i's in them. Okay? So if you have something that looks like this, red is bad, that's too brown. So you just solve this like you're normally solving an algebraic expression. X squared equals negative 4. X equals 2 what? No, yeah, plus or minus. Plus or minus the square root of negative 4. Okay? So x equals plus or minus 2i. Yeah? Okay? If you solve a quadratic equation using the quadratic formula, which you have to remember is x equals negative b plus or minus the square root of b squared minus 4ac over 2a. Okay? So this thing would not factor if you tried. Okay? So if you, and also, does it factor?
Yeah,
No, it doesn't.
maybe negative 5 and then positive 3. Right, I know, but the positive 3 is at 3x squared.
Oh, let's see. It does that.
It does
Yeah,
factor.
what-
Boom!
Yeah.
No.
5 would go with 3.
Yeah. Minus 5 plus 1.
Minus 5 times
Yeah.
1 is negative 5, not positive 5. Okay, so it doesn't factor. Okay?
This negative one.
Yeah, it would have to be a neg, right? Because
Are we gonna have to use a lot of quadratic?
not just a couple at the end. Okay? And so it doesn't factor, so if you were doing this, you get x equals negative b, which is what? 2, plus or minus the square root of b squared, which is 4, minus 4 times a, which is 3, times c, which is 5, the whole thing divided by 2 times 3, which is 6. And then you simplify this. You guys are advanced, you should be able to simplify these, okay? Square root of 4, what's that? 4 minus 60 is negative 56 over 6. Is there a perfect square in 56? 4 times, because 4
Yeah,
times
4 times 14.
4 times 14, very good. So you could rewrite this as 2 plus or minus 2 square root of negative 14 over 6, which is equal to 2, you can cancel out a 2 from everything. So you're allowed to factor out a 2 and turn this into a 3, turn that into a 1, get rid of that, turn that into a 1. So you get 1, x equals 1 plus or minus square root of 14i divided by 3. Okay? So people always get stuck on that. And I think that's everything we need to know. I think, let me just check. Should I go too fast, too slow, too medium?
Too many,
Okay. Too many? What happened? So, right, Irene, let's see if we got it right.
Wait, we did.
We got it right. There you go. You didn't try. Holy crap.
Look, it's 3.
That's a lot of stuff. You'll go pretty fast. You'll be okay. Yes, ma'am.
Do you have a chance